Okay, let's continue our discussion on renormalization group equations. So let me remind you what we have done so far. Okay, here. So you see the first equation here. This one. This was based on. So where is that? Yeah, this one was purely based on dimensional analysis. Okay, so we had scaled all the momenta by a factor of s. S is a dimensionless number. It could be 2, 10 or 1000 or whatever. Okay, so you are scaling all the momenta, and then the renormalized Green's function, okay, it satisfies this equation. And also we had already seen the renormalization group equations, which is given by this equation. This is what the renormalized Green's function satisfies. Okay, where the gamma phi is the anomalous dimension of phi. Okay, and then we had eliminated mu from these two equations, the derivative of mu, and then we had found this equation. Okay, which is s d over ds. You can write delta over delta as a partial derivative. Okay, in fact, it will be better to write it as a partial derivative, because there are many arguments. So I mean that I'm only differentiating with respect to s, keeping others fixed. So you have so s del over del s, and then you have a derivative with respect to renormalized coupling. It accompanies a beta tilde. Okay, and then you have a derivative with respect to renormalized mass. Okay, and you have mr, which is multiplied with 1 plus gamma m. Okay, so you see that if you had no renormalization, no need for renormalization, if there were no infinities, then the gamma m would be 0. Okay, if you go back and see, then from the definition of gamma m, you will see that it will be 1, because it involves derivative of z, and z to the lowest order is 1, so that will be 0. So this term would be, in the absence of renormalization, would be just mr del over del mr. Okay, and that is what this 1 is. So if gamma m is 0, it is just 1 here. So mr del over del mr. But if you need renormalization, then gamma m is non-zero, and this mr changes by mr gamma m. Okay, and here you have similarly minus n d phi tilde plus gamma phi, and again if no renormalization was required, then z phi would be 1. Remember, z phi is given by this. So z phi would be 1. If you don't require renormalization, then you can take phi to be phi r. Okay, then gamma phi would be 0, again for the same reason, that it involves the derivatives of z, and z is just 1, so that gives you 0. And here you would have just minus n times the dimension of phi tilde. Okay, but in the presence of renormalization, when there are infinities, this n times d phi tilde gets modified to n times d phi tilde plus gamma phi. So that's a contribution coming from the fact that there are infinities and we need to renormalize. Okay, so that is the equation we had obtained last time. And remember, mu is fixed. We are not changing mu anymore. The derivatives with respect to mu are gone, and we can work with a fixed value of mu. Okay, so we'll start from here. Let me just copy it. Okay, this is what we had. Also, I can remove these other things. Okay. So that's what we had, and now I will define gamma tilde m to be gamma 1 plus gamma m. Okay, and there's the definition, and d phi tilde, which is the dimension of phi tilde in 4 dimensions. And we are in 4 minus 2 epsilon dimensions. So this d phi tilde plus gamma phi, okay, this is what we define as gamma tilde phi. Okay, so this is the anomalous dimension, and gamma tilde phi is anomalous dimension plus the canonical dimension. Okay, the canonical dimension that you get by just counting the mass dimension of phi tilde. Okay, so these are the definitions. So our equation becomes, with these definitions, S del over del S minus beta tilde del over del lambda R gamma tilde m mr del over del mr minus n gamma tilde phi. Okay, so now I have all of them as tildes. Okay, all of them have tilde. G tilde n renormalized ski lambda r mr mu. Okay, that's the equation that we have. Okay, and what I want to do is I want to figure out how these Green's functions behave at large momenta, meaning I want to take large values of S. So how I can relate it to a Green's function at how I can relate Green's functions at lower energies to Green's functions at higher energies, right? Because this is a differential equation in S. Okay, and the solution of this will give you an expression relating Green's functions at different energy scales. Okay, so that is what we want to do. So this is a first order linear homogeneous partial differential equation for G tilde n, and that is what I want to solve now. So first thing that I do is, this is not nice that the sign of this is different from the sign of this one. Okay, so I will change the sign of this and make it plus, and you will see why that is something I want. So for that I do a change of variable. From S to T, where T is minus log S. That's just a change of variable. T will be T, just like S is a scale, T is a scale. The relation is this. So what is del over del T? This is minus S del over del S, that you can check. And of course S is equal to e to the minus T. So if I take the exponential on both sides, S is e to the minus T. Okay, so I will substitute this and this in the previous equation, which will give me del over del T plus, so what I'm doing is del over del S is minus del over del T. Okay, so that, and I'm then multiplying this entire equation by a minus sign. So you can multiply this entire equation by a minus sign. This will give you minus S del over del T, sorry, minus S del over del S, but minus S del over del S is del over del T. That is what I have written here. And because I have multiplied by a minus sign overall, this changes the sign. So it's beta tilde delta over delta lambda R. This changes sign. And this also changes sign. Okay. No. So S is e to the minus t now. Here I should instead of S, I should write e to the minus t. Okay, so this is fine. Now let's search for the solution, and for that I am going to introduce two new quantities, okay, which are called running coupling constant or effective coupling constant, and running mass or effective mass. Okay, so let us carry this equation to the next page so that we know what we are trying to solve. Okay, that's what we want to solve. To solve this, just to remind you again, what we will find is the Green's functions at scaled up momenta related to Green's functions without scaled up momenta. Okay, that is what it will do. So now the scale is t. Okay, instead of S, the scaling variable is t. Okay, so to solve this equation, let's introduce just a second. Okay, so I will introduce new quantities. Okay, which are called running coupling constant. Okay, this is something new that I'm going to define. It has not been already. So the coupling constant that we have been talking about till now, lambda r at mu. Okay, this is a coupling constant with, when you give a value of mu, you get a value of lambda r. Okay, so when you do an experiment, you choose a value of mu, okay, and through experiments you can find out, given that choice, which is arbitrary of course, given that choice of mu, what are the values of lambda r and mr that will reproduce your physical observations. Okay, but the running coupling constant which I am introducing is something different. It is not lambda r mu. Okay, that's a new object that I am going to define, and you should ask what is the definition of it. Okay, so that's one thing I'm going to define, and another thing will be running mass or running mass parameter. Okay, just like mr, this is also not a physical mass, right? Because mr is not physical. What is physical is the physical mass is obtained by the pole of the propagator, right? That we have seen, and how to get physical mass in terms of renormalized mass and renormalized coupling constant. And similarly, this running mass parameter you should not think of as physical mass. Physical mass is always obtained by looking at the pole of the propagator. Okay, so that is not something you should confuse with. So okay, so what's the definition of running coupling constant? So or also it's also called effective coupling constant. And this is also called effective mass. Okay, parameter. So I'm not going to give you a direct functional form of these running coupling constant and running mass parameter. Rather, the way we define it is through a differential equation that this satisfies. Okay, a first order differential equation that this satisfies the running coupling constant and the running mass parameter, and specify the boundary condition. Okay, once you have specified the boundary condition and given the differential equation, the solution is unique. Okay, and that you can solve to get that function. So we will define it through the differential equation and the boundary condition. So running coupling constant is denoted by lambda bar. It's a function of t. Okay, that is by definition a function of t, and this thing is m bar, a function of t. Okay, I'm not going to put any subscript r here. Okay, because there is no need. These are anyway finite quantities. Okay, so there is no need to put r or whatever. There is no corresponding bare thing defined, so there is no need to put r as a subscript. So what's the definition of lambda bar? The differential equation that lambda bar satisfies is the following. I mean, this is the definition. I'm saying it has, by definition, it satisfies this differential equation. Okay, it doesn't follow from something else. It is definition that I gave. So delta lambda bar over delta t is equal to beta tilde of lambda bar t. That's the differential equation it satisfies. And of course, giving a differential equation only, even though it's first order, doesn't solve it completely unless you specify boundary condition. Okay, so the boundary condition is that lambda bar at t equal to 0 is equal to lambda r. Okay, and I'm going to suppress mu because mu we always keep fixed now. Okay, we are not varying mu at all. So lambda r at whatever chosen value of mu, which is not going to change in this entire analysis. Okay, so what is the boundary condition? That lambda r at t equal to 0, meaning at 0 scaling, should be equal to the renormalized coupling constant. Okay, and this is the differential equation that it satisfies. So you see that when you solve it, you will get lambda bar of t, and the solution will contain lambda r. Okay, whatever that lambda r you have chosen. So I'm making that dependence explicit here now. Okay, so lambda bar of tr. Okay, this is what is your lambda bar of t. Okay, I've just used the fact that this will enter the solution of lambda bar. Okay, so I'm just indicating that by making it a part of the argument. So I will also just rewrite this defining differential equation using this fact. So delta lambda bar t lambda r over delta t is beta tilde lambda bar of t lambda r. Okay, that is our defining equation. I could have written this one first, okay, without doing this way, but just wanted to convey how lambda r comes about. So this is the defining equation of the running coupling constant. Okay, and similarly, I will give the definition of m bar of t, okay, the effective mass or the running mass, and it is defined by the following differential equation: del m bar t lambda r, okay, over delta t minus 1 over m bar of, you can put again t lambda r, okay. This is equal to gamma tilde m lambda bar t lambda r, okay. So gamma tilde we already know, it's a function of lambda r. That lambda r you replace by lambda bar, okay, and whatever you get sits here, okay. And this is the differential equation, and this is again by definition, it satisfies this differential equation together with the boundary condition that m bar at t equal to 0 and with this choice of lambda r is mr, okay. So these are the defining equations. Okay. No. Let me make it a little nicer. So here these two together and these two together. Okay, so now we have defined these two objects. Let's see how they can be useful in solving the differential equation. So in this equation here, maybe now that I am boxing, I will box this also. In this differential equation, I will replace wherever I have lambda r by lambda bar, and wherever I have mr, renormalized mass, I will replace it by m bar, meaning effective mass. Okay, and I can do so because this equation is valid for all values of lambda r and mr. Okay, so this replacement is allowed. So let's do that. Okay, so it's here again, and what I should do is replace lambda r by lambda bar of t lambda r and mr by m bar t lambda r. Okay, so I'll make this replacement of renormalized coupling and renormalized mass by effective coupling and effective mass, or running coupling and running mass. So what do I get? I get delta over delta t plus beta tilde, and beta tilde is a function of lambda bar. Okay, I will not write t lambda r again, I'll leave it like this, but that is understood. And then we have delta over delta lambda bar. Okay, because wherever you have lambda r, you replace by lambda bar. Minus gamma tilde m, and this written as function of lambda bar. Okay, we are working in the MS and MS bar schemes. Okay, or in short MS schemes. So gamma tilde was, remember, it is 1 plus gamma m, and we have already argued that gamma m, okay, and gamma phi, these do not depend on the renormalized mass mr or on the scale mu, right? In these schemes, the z's are independent of mu and mr. Okay, and that is why these are called mass independent renormalization schemes. Okay, so here this gamma tilde m will be a function of lambda, so that lambda I am replacing by lambda bar, and this mr I should replace by m bar. Then del over del mr will get replaced by del over del mr, del over del m bar. Okay, I want to make the arguments explicit. Let me just see. This is fine, good. So I'm making all the arguments explicit now. So m bar. So here mr is a function of lambda r, right? The renormalized mass is a function of renormalized coupling constant. Okay. So if I had written here mr of lambda r, which is something I should have done, made it more explicit, then you see when you replace it, mr by mr, the argument will get changed to lambda bar. Okay, and del over del m bar. Again, this has the same argument, lambda bar, plus n gamma tilde phi. Again, this is a function of lambda bar. Okay, this acting on g tilde n renormalized e to the minus t, these momenta ki, lambda bar, mr replaced by m bar, and mu I can drop, it is fixed. Okay, don't worry about mu, there is no mu here. Okay, so good, we are here. So let's see how we can write this. So if you look at the total derivative of time, total derivative of t, d over dt, okay, this is what? Del over del t, that's the partial derivative, plus del over del lambda bar, okay, and then you have del lambda bar over del t, okay, plus del over del m bar over del t. And what is this? This is del over del t, and we have defined del lambda bar over del t as beta tilde. So this is beta tilde of lambda bar of t lambda r. I'll just make it explicit. Okay. Now this term, del over del m bar. What is del m bar over del t? What happened? What is del m bar over del t? It is minus 1 over m bar, so you take that to the other side. So del m bar over del t is minus m bar gamma tilde. Okay, so it is minus m bar and gamma tilde. Okay, and again I should write those arguments. What happened? Gamma tilde of lambda bar, which is function of t and lambda r, and then you had del over del m bar. Okay, so if you see here, this is exactly the same thing, right? So del over del t here, del over del lambda beta tilde, that is del over del lambda beta tilde. Then you have del over del m multiplying gamma tilde multiplying m bar. You have del over del m bar gamma tilde m. So that's the same thing with the same minus sign. So these first three terms together become the total derivative of t. So d over dt, then you have plus n gamma tilde phi of lambda bar. Okay, and maybe I should write it nicely, plus n gamma tilde phi of, this is the argument of it, lambda bar, and this is t lambda r. Okay, this is the operator that acts on the renormalized Green's function, the endpoint renormalized Green's function. And the arguments are e to the minus t, ki lambda bar, t lambda r, and m bar t lambda r, okay, mu is equal to 0. So remember, we have chosen mu to be fixed, and that given that fixed mu, lambda r is a fixed object. Okay, and then right now you have these m bars and lambda bars, they vary with the value of t. Okay, so the variable here is t now. Okay, so as you change the t, the values of m bar and lambda bar change, keeping mu fixed, correspondingly keeping lambda r and mr fixed. Okay, so good, we have converted this partial differential equation to ordinary differential equation. Now let's integrate this out. Okay, this is what we have now. So let's integrate this. So when you integrate this, you will get the following. And okay, let me give you the solution and then we can check. G tilde n r e to the minus, okay, g tilde n r e to the minus t. Okay, remember this is just scaling. Okay, so you are scaling all the momenta, all the components by a factor of e to the minus t. Okay, lambda bar of t, I am suppressing or maybe I should not suppress, I'll just keep it. Then m bar of T lambda r, the redundant mu, is equal to GN R. So this is the solution, okay. We'll check why this is the solution. So you get Ki, so instead of e to the minus t, it's Ki, lambda r, not lambda bar, lambda r, mr mu, okay. As you can see, there is no t dependency here, so this is really coming from the integration constants times maybe here, let me try if it works, e to the minus integral 0 to t dt prime n gamma tilde phi, and the arguments are lambda bar, t prime, lambda r. Okay, that's the first bracket closing, and then this is the second bracket closing. So that's the solution. Okay, where lambda bar 0 lambda r, this is what we have used. Okay, that's what we have used. Now I will, okay, let me first show you that if I take this and differentiate, this satisfies the above equation. So let's take a derivative of the right hand side. Okay, so let's check. So take the derivative of right hand side. Okay, this does not depend on t. Okay, so that just comes out. So d over dt of the right hand side, which is GNR into this exponential. Okay, this is GNR times, you have to take the derivative of this object with respect to t. So let me just tell you on the other page. So what we want to calculate is something of this sort. D over dt of something of an integral from a to t, so where a is some constant, okay, of an integral of some function f of t prime. Okay, suppose you want to take this integral, the time dependence is here, and you want to take the derivative, what it will be. Okay, so this is just d over dt of integral. So let's call the indefinite integral of ft prime as capital Ft prime. So let's define dt prime ft prime. This is an indefinite integral to be f of t prime. Okay, that's by definition. So clearly f of t prime is the derivative of f. Okay, if you integrate, you get this. If you differentiate, you get this. So capital F is the integral of small f. So when you integrate this, you get capital F. Okay, and you should put t prime equal to a and t prime equal to t, which is d over dt of f of t. So when I put t prime equal to t, this becomes f of t minus f of a. Okay, and as I said, a is a constant. The only place where you have t is here. So this derivative drops out, and you get df capital F over dt. but the derivative of capital F is what is small f. Okay, so this is f of t. So what you get here is that if you have the time dependence sitting here in the limit of the in the limit of the integral, then after you differentiate, what you get is just the integrand, and the integrand is the f of t prime. So you replace t prime by t, and that's what you get. So f of t. Okay, let me write it as rough sheet. So that's what we are going to use here. So d over dt acting on this is g and r times derivative acting on the exponential. So derivative acting on the exponential is the derivative of the exponent times the exponential. So what's the derivative of the exponent? So right now you have integrand is minus n gamma tilde phi. Okay, and I should put instead of t prime t. That's what we have seen. So I get minus n gamma tilde phi lambda bar t lambda r. Okay, times this exponential again. Okay, which is minus n gamma tilde phi, I'll suppress the arguments, times g tilde n, this times this, right, which is again the original thing, g tilde n e to the minus t ki lambda bar m bar mu. Okay, taking this to the other side and remembering that this is exactly this factor, you get d over dt plus n gamma tilde phi, okay, acting on g tilde n e to the minus t ki lambda bar t lambda r m bar t lambda r mu equal to 0. Okay, so we have checked that this is satisfied. Okay, so you arrive at this equation. So indeed what I have given you as a solution is correct. Okay, so that's the solution of our equation here. Okay, we will call it Callan Symanzik equation, and that's the solution of Callan Symanzik equation. Okay, where is that? Here. So here is the solution. Now, okay, let's discuss the solution, and I don't think I will finish the discussion today, but in this video, but let's start it. So the solution to okay, this is what I'm calling, so same equation, this is what I'm calling Callan Symanzik equation. Okay, so the solution to Callan Symanzik equation is, what we have found is g tilde, yeah, so let me do one more step. Here, this is a solution. Now what I'll do is, I will change the scale, or rather just, I will take this exponential and put it on the left side. Okay, so that I get a relation for gn as an gn with argument ki in terms of gn in terms of argument e to the minus t ki. Okay, so for t positive, this is a lower scale. Okay, so I will be then relating a Green's function at some scale to a Green's function, to the same Green's function at a lower scale. Okay, so let me take the exponential to the other side and write the solution here. Okay, so it's the same solution but with the exponent taken on the other side. So G tilde N R okay. Remember, these are not bars, these are lambda R, M R and mu. Okay, these are not running couplings. Let me show you again. So here what you have doesn't involve running coupling or running mass. Okay, but the left hand side does. So I will take this exponent on the left hand side, which will become the right hand side now. Everything will involve running coupling constant and running mass parameter. Okay, so this is G tilde N e to the minus t ki lambda bar of t lambda r m bar of t lambda r mu times e to this integral. Okay, n is fixed, n is not function of these couplings. Okay, I will do one more step, which is a minor step. So instead of ki, I will define pi. So instead of using momenta ki, I will just call pi, which are scaled like this. Okay, so that ki is e to the t pi. So using this, I get G tilde N renormalized. Now ki is e to the t pi. So when t is positive and large, I am looking at a large momentum. All momenta are large now. Okay. None of these get affected. Okay, ki appears only here. There is no other place where ki appears. So it is going to change only here. Okay, no other place. So you get pi lambda bar t lambda r, or I will just suppress it. I will just write t, or maybe not. Okay, so you see that the Green's function at scaled up momenta is related to unscaled momenta, but the Green's function now here involves running couplings and running masses. Okay, instead of lambda r and mr, this involves running coupling and running masses, and also you have this exponential factor. Okay, so this is our equation, which satisfies the Callan Symanzik equation. I'll give it a nice color. Okay, some color, I don't know whether it's nice. Yeah, looks nice. So that's the equation, that's the solution, and let's analyze this. But before I analyze, I will write the same equation without all these details of the arguments. I will keep the arguments here, but also suppress these arguments in this expression so that it looks a little cleaner to see. So it's just e to the t p I lambda r m r mu is equal to G tilde N R. Okay, I wish I had suppressed these also. Anyway, so pi lambda bar of t, okay, which is really lambda bar of t lambda r, m bar of t, mu e to the integral 0 to t dt prime n gamma tilde phi lambda bar of t prime. Okay, that's the same equation with some suppression. Okay. So, so you see that now we have an expression of Green's function relating to different energy scales. Okay, and the thing that we have gained here is that on the right hand side, things are written in terms of not lambda r and mr, which are fixed once you have chosen a mu. Okay, there is nothing you can do to change them, but in terms of lambda bar and m bar, okay, which are a function of t now. Now, depending on what the value of t is, or equivalently how much you have scaled the external momenta, okay, these lambda bars and m bars will take some value. Okay, for different values of t, these will have different values because these are functions of t. Okay, and this might be useful. Okay, it might be useful if the coupling constant or the running coupling constant were small for large t. Okay, so if lambda, see, this is this object, this is still the Green's function, right? It's the same object as on the left hand side. So when you calculate, it's the same Green's function, but only difference is that where you had lambda r and m r, you are putting lambda bar and m bar. Okay, so as far as the calculation is concerned, it's the same calculation that you still have to do. But here the advantage would come from the fact that if lambda bar were to be small or very small, if you go sufficiently high in energy, meaning a sufficiently high value of t, okay, so that all external momenta are very large now, and if it were to happen that the coupling constant, at the running coupling constant, at those large values of t were to be small, if that happened, okay, then you are calculating the Green's function at very small values of coupling. Okay, and let's say you are looking at 4-point Green's function. Now 4-point Green's function, when you calculate, you have seen that you have all terms of order, you have to sum up all terms of order lambda r square, lambda r cube, lambda r 4, and so forth. Okay, all infinite terms. Now suppose at sufficiently high value of t, the coupling is very small, the running coupling is very small. Okay, and because only the running coupling enters here, if you were to ignore terms of higher orders, okay, it will not be a bad thing to do, because those higher order terms are going to be very suppressed because of your choice of t. Okay, because the lambda bar is very small there. Okay, we are assuming that situation that lambda bar is very small at high value of t. Okay, which could happen in some theories and could not happen in other theories. So that is the utility of it. Okay, you can then just use a lower order result. Okay, a result without going at higher orders in perturbation theory, and still get a good prediction by using this equation. Okay, because all the corrections are included in these gamma tildes and lambda bars, okay, basically here. Okay, so that's the utility of this equation. But before we say more, let's look at how the running mass or the effective mass changes with t. Okay, so that's the next thing we will do. So the question is, how does the effect, let's keep calling it running mass parameter run with T. Okay, T is the scale. Just a second. Okay, so let's find out how it runs with T. So the defining equation of m bar was the following. Which is, remember, gamma tilde is 1 plus gamma m. Okay, that's 1 plus gamma m. Okay, now suppose we didn't have to renormalize. Suppose there were no infinities. If there were no divergences due to the loop integrals, okay, then gamma m would be 0. Okay, that is what we have seen earlier. Then let's solve this differential equation for m bar in that case. Okay, when there are no divergences. In that case, del log m bar over del t will be -1. Okay, so here gamma m is 0, you have 1, so taking that minus sign to the other side gives you a -1, and 1 over m bar del m bar, that's del of log m bar. That's what I have done here. Okay, now you can integrate this and you get m bar is equal to mr e to the minus t. Okay, where I have used the boundary condition m bar 0, or let me make it more clearer, m bar at t equal to 0 is m bar. Okay, remember that was the boundary condition we had supplied together with this defining differential equation for m bar. Okay, so when you use it, you get this as the solution. Okay, so you see that the effective mass goes down as you increase t, okay, because this is e to the minus t. So if you take t to be large, meaning you are scaling up all the momenta, then the effective mass is going down. Okay, so and it's going down very fast because you have e to the minus t. Okay, that's a very rapid decay of this value. Now in general, gamma m would not be equal to 0, right? Because we will have divergences in the loop integrals, ultraviolet divergences in the loop integrals in general. Okay, so in that case, the result m bar will be will not be mre to the minus t, but it will be the following: m bar t lambda r would be mr exponential minus t. This is still this result, but then a correction due to the effect of renormalization, which is this. So you can integrate the above equation and you'll get the following. Okay, this is lambda bar t prime lambda r. Okay, so that's what you get in general. So this is the behavior for mass. So this is something, you see, this is still something rapidly decreasing, but then there are modifications. Okay, so that's good. Then so let's say, let's again look at the case when there were no divergences. If there were no divergences, then I have already seen that m bar would be just mre to the minus t. Okay, so in this case we require, I'm just repeating whatever I said earlier. Just a second. Okay, sorry. So what is that? Yeah. If there were no divergences and we required no renormalization, then beta tilde would be 0. Gamma m, as we have seen, would be 0. Gamma tilde m would be 1. Gamma phi would be 0. And gamma tilde phi, which is d phi tilde plus gamma phi, that would be just d phi tilde. Okay. Remember what d phi tilde is. D phi tilde is the mass dimension of phi tilde. Okay, that is coming purely from dimensional analysis. Okay, you just count what is the mass dimension of phi tilde, that is what d phi tilde is. Gamma phi is the anomalous dimension of phi, and that is what we had called gamma tilde phi. Okay, so even when you put gamma phi to be 0, because the z's are 1, you still have gamma tilde phi equal to d phi tilde. Okay, now let's take this and put in the definitions of m bar and lambda bar. So we have already seen that m bar as a function of t is just mre to the minus t. Now let's look at the behavior of lambda bar in this case. Okay, when you don't need renormalization. So beta function, beta tilde is 0 here, which means that lambda bar is a constant. Okay, that's the solution of this equation. And then lambda bar, when you put the boundary condition, lambda bar of 0, lambda r, that is lambda r. Okay, that's the boundary condition. Lambda bar at t equal to 0 is lambda r. Okay, so that constant is lambda r. So that's the solution. So you see that the effective coupling constant or the running coupling constant does not really run if you do not need renormalization, but still the masses, the running mass, it goes down. Okay, it decays rapidly with increase in t. Okay. Okay, so this will happen if you have a theory which is finite, where all the loops are giving you finite results. Okay, so let's put this in the solution for the Green's function that we obtain. Okay, and let's see what we get. So where is that? Here. Let me take this equation and put it on the next page. Okay, we have got a little bit of pink, but that's not going to disturb us. So if theory is finite, okay, no renormalization required, then what do we get? G tilde n renormalized at a large scale. I am taking t to be large, at these values of coupling constants NMR, okay, that is what you want to calculate, will be G tilde n r pi. What is lambda bar of t lambda r? So I have suppressed this lambda r here, but you know that that's there. So lambda bar t is lambda r. Okay. What is m bar of t? In this case, it is mr e to the minus t. Okay, t is large, so this is a very small number, mu. Okay, let's keep t to be finite but large. And then this thing here will give us into, so just a second again. Okay, so what I was saying was that let's look at the case where the theory is finite and doesn't require any ultraviolet renormalizations. Okay, in that case, G tilde n r of the scaled up momenta will be related to the Green's function without the scaled up momenta. And here, as you see, the mass is suppressed because you have e to the minus t factor, which is very small because t is large. Okay, so that's this, and then other factor is integral exponential to so gamma tilde phi is what? Gamma tilde phi in this case is just d phi tilde. Okay, just the canonical dimension of phi tilde. So it is integral dt, let me write this here, integral 0 to t dt prime of n d phi tilde. D phi tilde is a constant, it doesn't depend on t. Okay, n is a constant, doesn't depend on t, and this integral gives you t. So you get e to the t, okay, n d phi tilde. Okay, that's the result you get. Okay, so what it is saying is, think of e to the t as let's call it s. Okay, nu s. Okay, you can call it s. So it is just s times pi. So all the momenta I have scaled up by s times. Okay, then here you have in the argument this will become mr over s. Okay, because e to the minus t, that's the inverse of e to the t, so it will be 1 over s, and this is s pi. Okay, and here it is, this factor is s power n d phi tilde. Okay. Now you see, this result is what you would have gotten from purely dimensional analysis, right? See, Green's function is what? Green's function is this. So there is time order product, and right now this is the tilde version, meaning the Fourier transform of it. You are taking the Fourier transform of each of these x's. Okay, so you get phi tildes for each of them. Okay, so what's the dimension of this object? It will be n d phi tilde, right? Because each phi tilde will bring d phi tilde, and there are n of them, so you have n d phi tilde. Sorry, n d. Okay, that is the mass dimension of this object. Okay, and if you scale it up, these momenta which you get here in the arguments, if you scale it up, then based on the canonical dimension, you see that the object will scale up by a factor of s power the canonical dimension, which is n d phi tilde, right? So that is what would have happened. That is something you expected on the grounds of naive mass dimension counting. Okay, if you look at this Green's function and say, okay, I just want to see how things scale if I scale the momenta, okay, in the case of a finite theory, then you see that it is scaling just like scaling according to the canonical dimension of phi tilde, right? This object has mass dimension n d phi tilde, and it is getting scaled as s times n d phi tilde. Okay, that's the naive scaling that you expect, that you get. But this naive scaling based on these canonical dimensions is modified, okay, and because of the fact that you have this anomalous dimension and beta function and these objects non-zero, okay, because you require renormalization, and it is because of that effect that this naive scaling is modified to what you have here in the full expression. Okay, so let me just write it in words. So prediction of the scaling based on naive power counting is modified due to the renormalization effects. Okay, and as I have just told you, if renormalization was absent, then you do indeed get a naive scaling based on power counting. Okay, but this is the true result. This is in a special case of a finite theory. Okay, we'll discuss more about this solution that we have obtained in the next video.